All right, so I briefly mentioned before that, ODE has lots of applications and appears pretty much in every field that you can imagine. So let me mention a little bit more details. So applications of ODEs. Well, basically, as we said, ODEs naturally appear in different fields. Such as physics, engineering, biology, economics, and many other fields. So for example, population models. So suppose that P of T denotes the population at time T. So let's say if T is the independent variable and P of P is the dependent variable, P is our function, then P of T denotes the population at time T. Now this population could be population of anything. So could be population of people, or in biology could be population of bacteria or any other type of population. So rate of change of population, and normally rate of change of population is proportional to the population itself. Right? So if there's a higher population, then population grows faster. Lower population grows slower. So ODE, this can be written as dp to dt equals some constant k times p. Rate of change means derivative. So dp to dt, rate of change, which is derivative, we assume that is proportional to the population, so it can be written as some constant k times p. And we'll see later how to solve this type of ODE. So for now, I just wanted to show you that, these ODEs can appear naturally, but how to solve it, we will get into that later. Let me also show you one example from physics. In physics, Newton's law of cooling. So suppose that you put an object with temperature. Suppose that we put an object in a room temperature with temperature TE. So room temperature, let's assume that it has temperature TE. The object, however, the temperature of the object changes with time. So suppose that T of T denotes the object temperature at time T. So room temperature is fixed and is TE. Object temperature depends on the time. So for example, let's say you put hot cup of coffee in the room. So the temperature drops, right? So in the beginning, temperature is high, then it drops. The temperature is a function of time, but the room temperature, we can assume it's fixed. Then Newton's law of cooling. Newton's law of cooling states that the rate of change of object temperature is proportional to so how fast the object temperature changes. So that depends on not the room temperature. For example, let's say if room temperature is hot, but the cup of coffee is also hot, then it won't drop so fast, right? But if the room temperature is hot, but you put in, let's say, ice cube in the room, then the change in temperature is very fast, right? So the important factor here is not the room temperature, but the difference between room temperature and object temperature. So if the room temperature is hot, for example, and you put an ice cube, then the change is fast because the difference between object temperature and room temperature is high. Similarly, if the room temperature is very low, the room is cold, and you put, for example, a hot cup of coffee, then the change is very fast. Because again, the difference is high. It's proportional to the difference between room temperature and object temperature. In other words, we can say that dt to dt is equal to some constant k times t minus te. So I can say compare a cup of tea or a cup of coffee put in a fridge versus a cup of coffee put in a hot room. Which one the change in temperature is faster? When you put cup of tea in fridge, that obviously change in temperature is much faster because the difference between the cup of coffee temperature and fridge temperature is very high. But in the other case, the difference between a cup of coffee temperature and hot room temperature is not very high. So the change is also slower. So we can say that always the change in temperature is proportional to the difference between difference between object temperature and the room temperature. So this is a first order linear ODE. According to what we said, it's first order because the highest derivative appeared is the first derivative, and it's linear because you know, our unknown function is t here, and there is no power for t. So for t and its derivatives, they all have power 1. There is no power 2 appeared, for example, or there is no square root appeared. So I gave you 2 examples of first order ODEs appeared in physics and in population models. So let's look at also an example of a second order ODE. An example of a second order ODE. So basically Hooke's law. If a spring is stretched by x centimeter, is stretched by x centimeter, then we can say that F is equal to Kx. And here, F is equal to MA, and A is equal to second derivative of X. So we can say that M d squared X dt squared is equal to Kx. So here, X is our unknown function. And T is the independent variable. And this is an example of a second order linear ODE. And it's linear because no power. There is second derivative, but that's okay. There is no power. Second derivative is not raised to any power. And neither x. X is just raised to power 1. It's not raised to any power other than 1. So it's a second order linear ODE. Now, one important remark I want to mention about solving ODEs is that if you want a unique solution for an ODE, you need some initial conditions. How many initial conditions? Well, that depends on the order of ODE. If it's a first order ODE, then you need 1 initial condition. Second order ODE, then you need 2 initial conditions, and so on. Third order ODE, 3 initial conditions, and so on. So this is a very important remark that otherwise, if you don't have initial condition, then your ODE would have infinitely many solutions. Okay, so here I can mention this as important remark that generally ODEs have infinitely many solutions. Okay, infinitely many solutions. For example, this ODE has infinitely many solutions, or this ODE has infinitely many solutions, unless we put initial conditions. Unless we put initial conditions for our ODE. Specifically, if we put n initial conditions for an nth order ODE, then under certain conditions, that ODE will have a unique solution. Okay, so for nth order ODE, we need nth order ODE in general, it has infinitely many solutions. But if you put n initial conditions, still we under certain conditions I mentioned, certain conditions we'll see that later. So for example, such as continuity of the function. But we'll look at those technicalities later. But generally, the idea is this, that if you have n order ODE and n initial conditions, then normally you have a unique solution. But if you have, let's say, second order ODE, but let's say you have only one initial condition, then you still have infinitely many solutions. If you have two initial conditions and second order ODE, then you have unique solution. So for example, let's say x plus y prime equals e to the x with initial condition y of 0 equals 1, then this equation has a unique solution. But if, let's say, I say x plus y prime equals e to the x with no initial condition, then this equation has infinitely many solutions. Okay, or let's say m d squared x to dt squared equals kx with x of 0 equals v of 0 equals 2 has a unique solution. Because v of 0 means x prime of 0. So this has two initial conditions and it's second order with two initial conditions, so it has unique solution. Or another example, again, if you have, let's say, m d squared x to dt squared equals kx, this time let's say with x of 0 equals x of 2 equals 1. Again, this one has a unique solution. See, when it comes to second order ODE, then I have options. I have different options to have two initial conditions. One option is that I can say x of one number and x of another number. So that will be two initial conditions. Another option is that I can say x of some number and x prime of some number. That's also two initial condition, right? So then I have, for second order ODE, I have different options. I can have x at two different points, or x at some point and x prime at some other point. as my initial conditions. Okay, so I briefly mentioned about ODEs and what is an ODE. But remember we said that we have two important types of differential equations: ordinary differential equations, which is also called ODE. The other type of differential equations is called partial differential equations, or PDE. So second type of differential equations, PDEs, or partial differential equations. So partial differential equations can happen if you have a function of two independent variables. See, so far, we had one independent variable and one dependent variable. So we said that independent variable could be called t and dependent variable could be called x, or independent variable could be called x and dependent variable could be called y. So regardless of the notation, we had one independent variable, one dependent variable. But in multivariable calculus, you saw, or you will see, that you can have two independent variables and one dependent variable. So if we have a function of two independent variables, say y equals y of x and t. So here x and t are independent variables, and y is the dependent variable. Okay, and then if we have a differential equation that includes partial derivatives of y. So if we have this and suppose that we have a differential equation including partial derivatives of y, partial derivatives of y respect to x and t, then that differential equation is called a partial differential equation, PDE. So if you have a function of two variables, then we can talk about partial derivatives, derivative respect to x and derivative respect to t. Derivative respect to x means when you assume that t is fixed and you change x. Similarly, derivative respect to t can be defined. So if you have a differential equation that relates y with its partial derivatives, so that's the difference. If you have a equality that relates y and its partial derivatives, and the goal is to find y, then that's called a PDE, a partial differential equation. So again, the goal, similar to before, the goal again is to find the unknown function y equals y of x and t given a PDE. Given a partial differential equation, the goal is to find y. Now, an example of PDE in physics, a famous example in physics is the wave equation. The wave equation. So suppose that consider u equals u of x and t. You know, a wave function is a function of x and t, position and time. The wave function is a function of x and t. So meaning that if we fix x, then it will be periodic in t, and if fix t, it will be periodic in x. So the partial derivative in physics, it can be shown that the partial derivative, the partial differential equation that determines u is the wave function satisfies the following PDE. And basically, second derivative of u respect to t equals c squared times second derivative of u respect to x. So this is PDE for a wave function. And as I said, you know, it can be shown that the solution of this differential equation, the solution of this PDE is periodic in x and periodic in t. Periodic in x, we mean if we fix t, and periodic in t means if we fix x. And c is a constant here, right? So see that if you look at this equality here, this equation, the partial derivative of u respect to t is related to partial derivative of u respect to x. So there is an equality, there is an equation involving partial derivatives of u. So this is called PDE, partial differential equation. Okay, so our focus in this course is to solve ODEs, not PDEs. PDEs, you can learn about them in a different course, in a higher level course. But our focus in this course will be all about ODEs. So note that in this course, we will focus about ODEs. To learn about PDEs, please take a higher level course. We don't have a course right now in the college about PDE, so we can take it in UBC or SFU. Okay. Now, but try to provide some brief introduction about ODEs and about differential equations and about what you want to do in this course and just some very general concepts. Now let's get into details. Let's start from chapter 1 from our book. Chapter 1. So now let's start officially. Chapter 1, first order equations. First order ODEs, basically. You know, remember we said we just want to focus on ODEs in this course. And the first section, 1.1, integrals as solutions. Integrals as solutions. So our goal is to solve a first order ODE. The goal is to solve a first order ODE. Right now, we want to start with the first order ODE of the form y prime equals f of x and y. Or y prime, I mean dy to dx. So again, x is the independent variable here. So y prime equals dy to dx equals f of x and y. We want to solve a differential equation of this form. Okay, now first we want to focus on some special cases of this type of equation. Now, when we say dy to dx equals f of x and y, that means any function of x and y could be, for example, 2x plus y, or just 2x, or just 2y, or x squared times y squared. It could be anything. But first, let's focus on the case where the function on the right-hand side is only a function of x, or only a function of y. And then we'll try to generalize that to more arbitrary cases. So first, so as the first step, maybe I can say as the first step, let's focus on equations of the form, let's say equation type 1 as in the form of dy to dx equals f of x, or second type, let's say dy to dx equals f of y. So for type 1, so given, let's say dy to dx equals f of x with the initial condition let's say y of x0 equals y0. Remember, we said that first order differential equation in general has infinitely many solutions unless you put one initial condition. If you have a first order differential equation with one initial condition, then you can say we have a unique solution. So in order to guarantee that we have a unique solution, because we have first order differential equation, we need one initial condition. And let's assume f is continuous as well. Remember, we said under certain conditions, right? And I said that the condition is usually related to continuity of the functions. So let's assume that f is continuous. Suppose that f of x is continuous. Then the solution of this initial value problem or IVP. The initial value problem or IVP means a differential equation or an ODE together with the initial conditions. Okay, IVP means ODE with the initial condition. Then it's called initial value problem. So the solution of this initial value problem will be given by y equals integral x0 to x f of t dt plus y0. This function here in the right-hand side will be the solution for this equation and with this initial condition. Why do you think that's the case? Why do you think that this is a solution for this? So let me give you the proof. Proof in order to show that, let me call this equation maybe 2 star. In order to show that y given in 2 star above is the solution of our IVP, we need to show that 2 things. First, dy to dx is equal to f of x. And second, y of x0 equals y0. So when you want to show that a function is a solution of a differential equation, that means if you substitute your function into your equation, it satisfies the equation. So similar thing happened for algebraic equation. For example, let's say you have x squared equals 4, and you want to show that x equals -2 is a solution for this. See, let's say if x squared equals 4 and you want to show that x equals -2 is a solution. How would you verify that x equals -2 is a solution? That means if you replace x with -2 the whole squared, it will be 4. So it satisfies the equation. But x equals, for example, 3 is not a solution. Why? Because if I replace x with 3 squared is 9, which is not 4. So x equals 3 is not a solution. Okay, so here if I want to show that this function here is a solution for this equation, that means if I replace y here, dy to dx must be f of x and y of x0 must be y0. Okay, so please note that here, by the way, when I say y, I mean y as a function of x. So to emphasize, I can say y of x equals this. Y as a function of x is equal to this. Now, to verify one, recall that FTC, we want to use FTC or Fundamental Theorem of Calculus, part 1, states that if f of t is a continuous function, then we can say that integral x0 to x f of t dt is a differentiable function Normally, this is denoted with capital F of x. In math 114, let me call this one capital F of x. Capital F of x equals integral x0 to x f of t dt is a differentiable function, and derivative of this capital F is equal to small f. So this is basically FTC. That if you have a function small f of t as a continuous function, then capital F of x, which is also called area function, this capital F of x is called area function, and defined this way, will be differentiable. So if small f is continuous, this capital F, or called area function, will be differentiable, and derivative of this capital F will be small f. So in our case, this is called FTC part 1. There was also FTC part 2, which helped you to find definite integrals, but FTC part 2 can be proved using FTC part 1. Now, so in our case above, what can we say? In our case, if we set y equals y of x equals integral x0 to x f of t dt, then y is differentiable function, y is a differentiable function. Since f of t is assumed to be continuous, and what is derivative of y? And dy to dx is equal to f of x. This is what we said here. Instead of capital F, we are calling it y here, but we are exactly in the same situation. Okay, so we showed that dy to dx equals f of x, which was our first goal, dy to dx equals f of x. And to prove the second condition, to prove 2, we need to calculate y of x0. How much is y of x0? We need to show y of x0 is y0. Y of x0 is easy to calculate. How much is y of x? Here, y of x is integral x0 to x f of t dt plus y0. So y of x0 will be integral x0 to x0 f of t dt plus y0. So this one by equation 2 star, we can write it as integral x0 to x0 f of t dt plus y0. And integral x0 to x0 is always 0. So this is 0 plus y0, and this is y0. Well, that's it. So this was the proof of second condition. So that means 2 star above is the solution of our initial value problem. Okay, so let's look at an example. Find the solution of, let's say, y prime equals x squared with y of 2 equals 3. So the solution is according to 2 star above. According to 2 star above, what can we say? We can say that y is equal to y of x is equal to integral x0 to x. Remember, it was integral x0 to x f of t dt plus y0. So integral x0 here is 2. So 2 to x f of t, which is t squared dt plus y0. Y0 is 3. Well, it's easy to calculate. We just need antiderivative of t squared here. Antiderivative of t squared is t cubed over 3. You saw this in math 114. Then we have to calculate between 2 to x plus 3. And then this is x cubed minus 2 cubed divided by 3 plus 3. And this is x cubed minus 8 divided by 3 plus 3. x cubed minus 8 over 3 plus 3. And if we simplify this, then we can write this one as x cubed over 3 minus 8 over 3 plus 3. And this can be written as x cubed over 3 plus 1 over 3. So this is our final answer. This is the solution of our ODE, or our initial value problem. Okay, so we learned how to solve differential equations of the form y prime equals f of x. And that type of differential equation needs only one initial condition. Let's say something of the form y of x0 equals y0. And we simply use FTC to find the solution, because FTC tells us that the area function, if you have a continuous function f, then the area function, and in that course you call it capital F, has the feature that capital F prime is equal to small f. So we just took advantage of that, and we found this solution. And basically this part is the area function. And then we just adjusted, because we needed the initial condition at x0 to be y0, but this function at x0 is 0. So we just need to simply add it with y0 in order to adjust the initial condition in order for y to be y0 at x0. Okay, so this can be applied, this formula can be applied basically for any continuous function small f, and then you will have a solution for your differential equation. Okay, guys, so that's all for today, and next time we will look at some more examples and other types of differential equations, first order differential equations. Okay, guys, thank you, and see you next time.